Here we're doing back propagation on some multi-layer neural network. It's kind of complicated, so let's try to get it right. Suppose we are at some layer L, so any L, and we want to find the derivative of the cost function with respect to some weight in layer L. Then we want to start with the activation in the previous layer. Maybe there are two of them, although their independent is not that useful. And they are connected like this to the layer L linear combinations. And of course, there may be multiple. Again, they are not related. But let's write two of them so that it looks like a network. So the same layer activation. Note that there are no crosses because this is just the activation G. It's not linear combinations. And let's do another one. And this is ZL plus 1, Z2 L plus 1. Okay, so we are trying to figure out the derivative with respect to this weight, say L. If we do back propagation, we need to go back, so we want to go here and go here. Somehow there are two or maybe more of them actually that are connected with this. So when we find the derivative of this, we actually need to sum up all of these things. So it's kind of difficult. Let's first start with one of them. But before that, we need the information from the next one. So we'll kind of do some kind of backward induction. So assume we know the answer for the next layer, we just get some relationship between this layer and the next layer. So when we differentiate with respect to the next layer stuff, this is say 1, 1. Remember the formula, if you check the previous few slides, it's this multiplied by A1L. So similarly, we can get another one, W, which one is this? This is 1 to 2 layer L plus 1. So let's actually write it down here. 1, 2, L plus 1. And this one is W1, 1, L plus 1. Okay, so this is delta 1, 2, L plus 1. And this is also A1, it's not A2, because we're not interested in what happens in the other unit. We are only interested in the first unit here. And so on. So in general, if you replace this by J, then this is J and this is J. Okay, so that's that. Let's move in another direction. Let's write down the chain rule with respect to L1, 1, W1, 1L. So this, again, is just the original derivative. Where can we start at? So we don't want to start here because it's past this derivative, so we want to start at this point. So say Z1L plus 1, and then we have this with respect to that, so going back this chain, AL, and then going back this chain, A1L, Z1L, and then finally we have the thing we want. What was this? ZL, W11L. Okay, so this is not right because we have the other ones. We need a sum. So we add a sum here, maybe indexed by J from 1 to whatever number of stuff in the next layer. We call it ML plus 1. And which ones are changed to J? This one must be changed to J. This one is J. What about this? We don't need the other ones, so we only need the A1 thing. So, okay, so that stays there. So let's begin with the easiest one. This with respect to this, Remember, it's linear combination, so it's just the activation. So this part becomes, say, A1L minus 1. What about this part? This part is A and Z relationship. Remember, there's the trick for logistic, logistic activation functions. It's just the activation multiplied by 1 minus the activation. So that's that. And now going back to this, what is this? This is W because again, linear combination, when you differentiate with respect to this, you get that. When you differentiate with this, you get the other one. So this is W11L plus 1. However, this is J, so one of them needs to be changed to J. That one needs to be changed to J. So it's 1J. And what about this? So this thing, we can somehow get it from this kind of relationships. So this is C with respect to one of these weights, you get an extra term, that's the activation, because again, it's linear combination. So without that derivative, the previous part would be this. So this whole thing would just be that. And as I said, replace 2 by J, you get the general version, this. And we have our sum, L plus 1. So now we have our expression. Because we're trying to do induction, so this must be equal to some kind of delta L. And remember, this form should hold for every layer. So for the next layer, it looks like this. For this layer, it must look the same. So this should look like a delta 1, 1 at level L multiplied by A1 level L minus 1. Okay, so let's change this a bit. This 2 would cancel out, so we're left with delta 1, 1 is just sum L plus 1, and this is 1J and W1J L plus 1 A1L. We get the recursive formula. Basically, we are expressing delta at level L, at layer L, as a function of delta at layer L plus 1. So if you check this formula, it's the same as the one I got on the slides. So basically, this is all we need to do. So given the last layer delta, we can just go back, find all the previous layer deltas, and given the deltas, we can just multiply it by the activation to get the gradient with respect to every weight in every layer.